B1, right? So this right here now is again another equilibrium problem. Sorry, not equilibrium, titration problem, right? But now in this case right here, right, we're given, a hypothetical acid, right, HZ, in this case right here. And so what we're doing in this case, right, is that we have a solution of 100 milliliters of HZ where we don't know what the concentration is, which is a very common thing to use titrations for, is to figure out what's going on. And so you then titrate it with whatever you need to be, right? So if you know it's an acid, right, you're going to titrate it with a base, which we're doing in this case with 0.100 molarity NaOH. And we're going to do it until we reach essentially the equivalence point. There's different ways to figure out when you're at the equivalence point, right? pH meters, acid base indicators, right? If you ever did a titration in high school or whatever, I don't know if you guys do them. Well, you guys didn't do them this year in lab, right? Because it's all like digital. So you may have watched one. But you didn't actually physically do it yourself, right? But there's, if you ever do it with like an indicator, right? That's when you're like, okay, right, the volume that you've added when the color changes, right? So phenolphthalein is an extremely common one, right? There's, methylene blue and all these other things, or methyl blue, right? So in this case right here, right, it took 40 milliliters of NaOH solution to reach the endpoint. And so again, right, endpoint, equivalence point, same thing, right? Endpoint is just simply, right, that's when your titration stops, because everything post that, right, is just simply then based off of the concentration of, the NaOH, right, the titrant that you're adding, or whatever. And so, you don't have to necessarily think about that. But again, what I'm going to do here is do something that I, suggested doing, a second ago, right, for B5, is when you start any of these titration problems, always draw out what the titration should actually look like and figuring out what equations you should be using at the different points, because then that way it'll make your life a lot easier, because then you just simply have to refer back to it, right? So in this case right here, what we're doing is a weak acid strong base titration. Right, and so if we look at this right here, right, and we have our pH. So in this case, and then volume NaOH added along the x-axis. Right, starting off, you're going to have a low pH, and then you're going to reach a plateau thing, and that is then going to shoot up dramatically, and then it's just going to go up. In that case, up. Did that all get deleted out? Weird. Right, so you have this right here, right? So this right here is going to be your initial. Why doesn't it like? This is going to be your initial point, right? And so this is going to be HZ dominant. And so that's going to be the point where you're going to be doing a weak acid equilibrium problem. This region right here, right, is going to be the buffer region. Right? And so that's going to be for the Henderson-Hasselbalch. It's appropriate to use. Sorry. And then halfway point, right here, during that titration, right before you reach the equivalence point, right, that's when the pH is going to equal the pKa of your system, right, of your weak acid. And then right here, right, that's going to be the equivalence point. And so at that point right there, right, Z minus becomes dominant species, right? And then up here, right, OH minus is going to be dominant, right? Post titration, right? It takes, a minute to do, but it makes approaching all subsequent problems a lot easier, right? Because you can just simply refer back to that, right? And think about, okay, well, where am I within the titration? Why does all of this matter? So the first question, right, that we're presented with, right, what is the original concentration of HZ? So we can easily figure that out, right, because we know how many moles of NaOH were required to completely neutralize that HZ, right? Because that's what's happening at the equivalence point, is that you've completely neutralized the acid, using the strong base at that scenario, right? And that's going to mean that the number of moles of NaOH at that point is going to be equal to the number of moles that you had started with in that scenario, right? And we know how many, we know the volume of NaOH that we added. We know the concentration of NaOH that we had added. And so using those things, right, we know what the volume initially of the HC was, right? And so knowing all that information, we can then easily calculate the number of moles of HC. We know the volume, right? And then divide the two, and then we get the concentration in those cases. So first things first, right? The moles of NaOH, right, is going to be equal to the concentration of NaOH, so 0.100 molarity, right? And I'm just going to rewrite molarity for my own sake as moles over liters, right, because that's what molarity is. I'm going to multiply that then by the volume, and so that's going to be 40 milliliters, so 40.0 milliliters, right? And so then to make the units work, right, I'm going to do 1 liter per 1,000 milliliters. So that way the milliliters cancels, right? Liters cancels, and all we're left with is moles. So if I take that, right, so 0.1 times 40 divided by 1,000, what I get is 0.004 moles, right? So that's how much NaOH was required to completely neutralize the HC, right? And so that's going to be then the number of moles of HC that we have. And so now to get what the concentration of HC was, initially, right, all we have to do is simply take the moles of HC, right? So 0.004 moles divided by the volume, right? So that's 100 milliliters, right? And so then in this case right here, right, we just simply multiply that by 1,000 milliliters and divide that by 1 liter to cancel out the milliliters. So we get moles over liters, which is what molarity is. So we have 0.004 divided by 100 times 1,000 gives us a concentration of 0.04 molarity. Right? And I would say, right, in terms of sig figs that I'm presenting here, even though sig figs, right, don't matter for the thing, I'm just going to keep them here, right, just for simplicity's sake. So that way there's 3 sig figs in that case, right? And so that's how you calculate the initial concentration of HC, right? We know that at the equivalence point, the number of moles are going to be equal. We can easily figure out then how many moles of HC we have. We know what the initial volume was. Divide those two, we get the initial concentration. So now the question is, the pH of the original solution was measured to be 4.46. What is the Ka of HC? So the initial solution, right? We know that we're at this point right here. And we know that HZ is dominant. So that means that the dominant reaction that we have happening right now at this point that we're trying to calculate, right, is that HZ aqueous plus H2O liquid is in equilibrium to form Z minus aqueous, right, the conjugate base, plus H3O plus aqueous in this case, right? So we have this right here. We know what the initial concentration is of our HZ, right? So we can set up our ice table. So in that case, what we have is initial concentration of 0.0400 molarity, right? We have the waters don't matter. The Z minus, right, starts off with 0. H0 plus starts off with 0. We lose X of HZ. We gain X of Z minus. We gain X of H3O plus. And so that means then at the end of that equilibrium, right, we have 0.0400 minus X concentration for the HZ, and we should have X for Z minus and X for H3O plus. So if we set up the equilibrium expression in this case, right, we have Ka is equal to the concentration of Z minus times the concentration of H3O plus over the concentration of HZ in this case right here, right? So we have all of that. Now, the question is, what is Ka, right? That's what we're trying to calculate in this case. And so the thing is, right, if we know what the pH is, because we can use like a pH meter or whatever, right, to measure what the initial pH was, we can figure out then from there what the Ka is, because we know what X is in this scenario because we have the pH, because the pH, right, is equal to the negative log of the concentration of H3O plus in this case. So if we're trying to figure out what the concentration of H3O plus is, right, we just rearrange this right here, and so we get the concentration of H3O plus is equal to 10 to the power of the negative pH, right? And so if we plug in our value, right, so we have 10 to the power of negative 4.46. So what that gives us is the concentration of H3O plus is equal to 10 to the power of negative 4.46, 3.47 times 10 to the negative fifth molarity, right? So that's the concentration of H3O plus that we have in solution, right, starting off. And we know, right, based off of our ice table, that that's what's going to be equal to X in this case. So if we know that that's equal to X, we can just plug that in to all of our different values, and then we can calculate what Ka is. So if we go here, right, what we had is, right, X over 0.0400 molarity minus X. So if we plug in our X value, what we have is, what is it, 3.47 times 10 to the negative fifth squared over 0.0400 minus 3.47 times 10 to the negative fifth. And so what we get now is X squared divided by 0.0400 minus X. So what we get is 3.01 times 10 to the negative 8, right? So that should be the Ka value. So this is B1, 3.01 times 10 to the negative 8, right? So one thing I did, just as an easy thing, so if you have a value, right, that you can just simply do, right? So if you have a TIA calculator, you can just simply use the store button, which is, where is it? The store button, which is like right here, right? You can do store button, and then you can click on the X button for, like, that's what I just did for, instead of having to type in 3.47 times 10 to the negative fifth, right? I just simply stored it as X, and then I just simply put in, X squared divided by 0.0 whatever minus X and stuff like that, right? So that's a very easy way to quickly do that instead of having to retype this stuff in and accidentally making mistakes in those scenarios, right? So that's a little tip in how to use your calculator in case you're not aware, right? But that's how you get the Ka in that case, right? Because we know the pH of what we're looking at, right? So we can get the Ka that way, and then and so we can use all of that information in those scenarios. So that's how you do part B of B1. So part C, right? So now the question is, what is the percent of HC that is ionized, right? And so we can just simply do that equation, right? So the percent ionized equation, right, is going to be essentially the the value of, or the concentration of Z minus divided by the concentration of HZ times 100% in that case, right? So in this case right here, what we had was that the concentration of Z minus was 3.46 times 10, 3.47 times 10 to the negative fifth divided by the concentration of HC that we started off with, which was 0.0400, and multiply that by 100%. And so what we get is 3.47 times 10 to the negative fifth divided by 0.04, multiply that by 1,000, not by 1,000, by 100, let me divide that by 10, right? So that comes out to being 0.087 or 68%, right? Yeah, which is what I have right here, 0.0867, 0.86, in those cases, right? And so that's what the percent ionized HC is that you have initially, right? It's less than a per mil, right? So very, very small amount of it. And so the next question is, right, what is the concentration of Z minus at the equivalence point? So going back, right, we know that at the equivalence point, the number of moles of HZ has been completely converted over into Z minus. And so if we know the number of moles that we started off with, which we were able to calculate in part A, right? So that's 0.004 moles. Right, so moles HZ initial is equal to 0.0400 moles, right? 0.0, no, there's 1 0 missing. Right, and so that's going to then be equal to the number of moles of Z minus at the equivalence point. The next question is the volume, right? So we have to add up the volume that we started off with. So initial volume was 100 milliliters plus, and so what we added was 40 milliliters of the NaOH solution plus 40 milliliters. And so what we get then, I can just do this math in my head, is 140 milliliters, right? And so that right there is the volume that we end up with. And so now if we want to calculate the concentration of Z minus at the equivalence point, so that's going to be Z minus is equal to 0.00400 moles divided by 140 milliliters. And this is then going to be multiplied by 1,000 milliliters divided by 1 liter, right? Because that way milliliters cancels and you end up with moles over liters. And so we have 0.004 divided by 140 times 1,000 comes out to a concentration of 0.0286 molarity, right? Yeah, which is what I have on the key. Right, and so that's what the concentration is then of Z minus at the equivalence point. So the final question is, what is the pH at the equivalence point? And so now, right, knowing what we know, right, again, going back to that plot that I have right here, at the equivalence point, the concentration of Z minus, right, is the dominant species, right? And so that equilibrium, right, the base dissociation equilibrium of Z minus is going to be the dominant reaction that happens. So now what we can do is simply write out what that reaction is. So I'm just going to simply, right, do that right here, right? So we have Z minus aqueous plus H2O liquid is an equilibrium to form HZ aqueous plus H3O. Nope, not H3O plus. OH minus aqueous in that case. Right, so we have that right there. So we can set up our ice table. Right, so Z minus, we start off with 0.0286 molarity, right? H2O can be all ignored, right? We have 0 initially of HC, 0 of OH minus, right? That's how we're going to approach it. So we lose X of Z minus, gain X of HZ, gain X, of OH minus. So at the end, we have 0.0286 minus X, and then X of HC and X of OH minus in those cases. And so now we can set up the equilibrium expression, right? And so I'm going to do that down here, right? So that's going to be KB is going to be equal to the concentration of HZ times the concentration of OH minus divided by the concentration of Z minus. So we plug in our values that we have right here. We have, X times X over 0.0286 minus X. And that's now going to be equal to, right? And let me just change that X times X to X squared to keep it beautiful. Right, so we have X squared right here. Right, so that's going to be equal to KB. We don't specifically know the KB, but we know the KA because we calculated that in part B. So we can just easily figure that out because that's just simply going to be KW over KA. So now we have 1 times 10 to the negative 14 divided by, what was it? 3.018 times 10 to the negative 8. 3.01 times 10 to the negative 8. So we plug that in. What we get is 1 times 10 to the negative 14 divided by 3.01 times 10 to the negative 8. We get 3.32 times 10 to the negative 7 is the KB value, right? So we have that right there. So now we can solve for X, and we can do that by, again, first trying out the 5% approximation, right? So I'm just going to consider that X to be negligible. And so now, right, what we have is X squared is equal to, I'm going to simply multiply 3.32 times 10 to the negative 7 times 0.0286. So what I get is 9.450 times 10 to the negative 9. Take the square root of this. What I get is X is equal to square root of that answer is 9.74 times 10 to the negative 5th, right? And so that's going to then be equal to the concentration of OH minus, right? So we have the concentration of OH minus now. And if we have the concentration of OH minus, right, we can easily then figure out what the pH is because using the approach that I had, kind of shown, like derived in B5 towards the beginning, right, we know that the pH is going to be equal to 14 minus the POH. And we know that the POH is equal to the negative log of the OH minus. That means then that pH is going to be equal to 14 plus the log of the concentration of OH minus in this case. And so we can just simply plug in our numbers, right? So we have 14 plus the log of 9.74 times 10 to the negative fifth. And so what we get is the pH of the solution at the equivalence point is equal to 14 plus the log of 9.74 times 10 to the negative fifth, 9.99, which is what I have on the key, right? And that's what the pH is right here. And so that's how you approach B1, right? So again, very similar to B5. Only difference is, right, that we didn't know what the Ka was initially, but we were able to calculate it because we did the titration and figured out how many moles we initially had, and we knew what the pH was in those cases. And so very exciting and very cool stuff. So that's how you approach B1.